Hello, everyone. Shana, Shana. Hey, hey. I hope you're doing great. You had a great lunch. And ready for a little bit talking about continuous profiling. We'll talk first about profiling in general, and then we will dive into what continuous profiling is, which is TLDR. It's pretty similar, just to add continuous part to it. A little bit before that, the boring part, I'm Mohammed. I work for a Swedish audio streaming company, Spotify, and I'm also a community guy. And the reason I did this presentation is I'm a Java developer, and I'm also an on-call developer. I had to wake up to be here in the conference at 4 a.m., which is, yeah, flying. Waking up for flying is always a good reason, but waking up after an alert, being on call, is definitely not good. So, how many of you have been on call before? Okay, a few hands. So being on call is not pleasant, and waking up in the middle of the night trying to figure out what's wrong, trying to look at all the metrics, what is happening is not the best feeling that you can have. By the way, this presentation is going to be a little bit full of image generation from DALL-E because now it's easier to generate things, so bear with me. But before diving into profiling and why it is important, let's go back a little bit, go a step back and try to discuss how the mindset behind how the architectures that we have nowadays become more and more complex. So in the 90s and little bit before, we had monoliths, a simple flow of communication between the client and the service. All the components of the application, all the modules were tightly packaged together into a single executable, and that was deployed into the server, single flow of communication between the client and the server. It was working perfectly. And if something goes wrong, you just need to focus on that single component, turn it off and on. It works every time. And then you call it a day. And then in order to scale, because going with monolith, scaling was really hard problem. So in order to scale, we started to break our monolith down into smaller applications. And SOA and service-oriented architecture was one of the first approaches in order to make our application smaller. And we needed some sort of communication and interconnection between all those components. And ESBs and service buses were basically the idea that came up with. The idea was legit, but the implementation and organizational challenges were very hard to operationalize. So turned out, even if the intention were good, how we ended up implementing those things weren't good. So we ended with more complexities, more challenges that we intended to do. And then in 2010, the Netflix wave with microservices, and then all other companies started to break our services even more smaller, which is basically decentralized communication, dump pipes, interconnecting a lot of services that basically collaborate together in order to achieve some functionality. That functionality can either to achieve some means, some objectives, deliver some value, or just to pass some simple data. And then with the rise of microservices, containers came in, that exploded in popularity, and then we went ahead into making and further breaking down application to smaller and smaller services, fast now and serverless and all of that. But software engineering and distributed systems follows what we call Murphy's Law, which says that anything that can go wrong will eventually go wrong. The more instances of anything we have, the more the likelihood that it will break. The problem when we move into distributed systems is when it breaks, there is the matter of unpredictability now, because the components no longer start and stop at the same time. Probably they don't have the same version even. So how we can face those challenges that are new with when we move it to distributed systems. So you probably already learned about it. There are operationalizing a distributed system is kind of challenging from an observability point of view, because you have those multiple components tightly packaged. So observing the interaction between all the services is trickier. Traffic management, doing things like A/B testing, blue-green deployment and all of that is more challenging when you have those multiple instances. You mentioned that it would blink, and it's blinked. But moving on, securing communication between those services, it's becoming more challenging when we have those loosely component services that are probably not having the same runtime. The runtime could be run in different languages, so how to secure those communication and add this layer of security across the whole fleet is more challenging. And then managing timeout and communication failures, again, especially if you have different runtime and multiple runtime. And then when it comes to risk assessments, there is a framework that we usually use, be it in defense, be it in human psychology. We tend to refer to the Harry framework, which differs the challenges into 4 categories: known knowns, known unknowns, unknown unknowns, known knowns, known unknown knowns, known unknowns, and unknown unknowns. Oh, bear with me here. I mentioned that I wake up at 4 a.m., so my brain is a little bit foggy. So there are 4 quadruplets. I mentioned only 3 here because those are the most important. In the context of software engineering, if you try to map it, what known knowns is a thing that's trivial to our system. You know that if you divide by 0, you will have an exception. If you try to call an object that is null, you will have a null pointer exception. Just as the obvious things that can be easily tracked. And then the known unknowns is the unexpected behavior of our system. Think of it like legacy behavior that is undocumented, and it happens every now and then for non-obvious reasons. So we spend a lot of time tracking that unknown behavior down, but we add logs and metrics and traces in order to have it. And then what causes the most incidents and wake up a lot of people during the night is unknown unknowns, things that we don't know about our system. And that's what causes generally the major incidents that we see in software engineering. And to face those challenges that we face in distributed systems in our industry, up until recently, we referred to 3 ways, which we call the pillars of observability. So we have logs, metrics, and traces. So very briefly, logs are time-stamped textual information that our system prints. They are easy to operate. Whenever we need some information, we just add a log line in order to track what's actually happening. They are super cheap to operationalize, super cheap to add, very easy. You just need to add those and basically track all those information, and helps to get understanding about what is happening. Basically, if you have a path and you want to understand how the flow is actually executed, you can add a couple of logs here and there, and then you can track the execution of that request in your thread or multiple threads. And then we have metrics. Metrics are basically quantitative numbers that we collect from our application, the infrastructure that it runs, and the resources that it runs on. And the KPIs for the metrics include CPU, memory, disk, I/O, latency, network, whatever. And it helps us to track what is happening and how our application is basically performing in real time. So if we have a latency spike, we can correlate it with different metrics. Probably there is a CPU increase, there's a memory increase, the garbage collector is behaving weirdly. So we can try to get to the bottom of the issue and see what is actually causing the issue. And then when we move it to distributed systems, we needed to track the request path of our requests. And their traces came in. And it enabled us to track the end-to-end interaction of our request. Given one request, we can check the path that it followed into different services. And that helps to track bottlenecks and understand where the latency came from by seeing where our requests spend the most time off during its TTL, during its lifespan, and then we can see what's happening, and then it gives a nice breakdown over where the application is actually spending the most of time. And then I was so super happy about the image that I generated with DALI and the pillars of observability. And then Jonathan Ivanov, which works at Pivotal, VMware, whatever that's called now, but it works in the Micrometer team, which is a great tool for observability, especially for GVM applications. Check it out if you have not. But he mentioned that the observability should not define with pillars, because no matter the amount of pillars that we have, they never can show the whole picture. But he basically means that we need to correlate those different metrics. You can't just isolate them and hope that we can basically get to the bottom of the issue. Correlating them help us to get an understanding about the performance and the health of our system. And then correlating them, we mentioned the 3 pillars of observability: metrics, logs, and traces. Metrics and logs, both of them help us to track the known nodes. If you have an exception, you can go to the logs, check the stack trace, and then you understand why it's actually happening, where it did happen, and probably hint why it's happening. If a network failure, you would have something like, oh, this call to the server failed, and this is why. And it'll probably go to the metrics and see the health of the other system, or probably could just be a hiccup. So it helps us to get an understanding about the known nodes. Adding traces will help us to understand the things that weren't obvious, but we can help us to track them down. Like the unknown patterns that we generally see that are not predictable. So adding traces and seeing the where the request basically went and how what is performant, what service called, help us to understand known unknowns. However, something that is missing is basically unknowns. How we can be more on the proactive side in order to detect bugs before they become major failures. So with logs and metrics, we have known patterns. So patterns, when there is an issue, we go to them and try to understand what is actually happening. But when the issue is involved multiple services, we include traces and try to correlate between the performance of all those applications. But when the pattern is unpredictable, it happens every now and then, profiles will basically help us to gain more data, more observability over how the system is actually behaving. And when we manage to decipher actually what's the issue is, then we can basically detect those anomalies and bugs before they become incidents. And then we add the necessary metrics, be it in the logs, be it in the metrics, in order to track down this pattern and bug and issue. So this is basically how we can correlate between them to cover all the quadruplets with that Johari framework mentioned in the context of software engineering. So profiling, you can think of it as the X-ray, right? When you go to a doctor, things like measuring your temperature, your blood pressure, it basically gives you the vital signals of how your human body reacts. If you are sick or not, you can basically detect that using that. But there are, to understand or to detect the more issues with your body, let's say, then X-rays would help to gain an understanding and go even deeper than those vital signals give. So profilers is basically the X-ray of how the system and our application is actually behaving and performing. And then there are multiple types of profiling, even beyond that list. But the most known ones and the ones that you should probably be already aware of, CPU profiling. What is consuming the most of my CPU? It helps you to understand why your application is consuming that much CPU, and probably can help you to understand why. Workload profiling, it understands why my application is taking that much time, be it CPU or something else. Could be spent in memory, could be waiting for a request coming in on I/O, could be blocked on anything. But workload profiling helps you understand why your application is taking that much time. Allocation profiling tries to understand where this allocation pressure comes from, why there is the application needs that amount of resources in order, especially memory, in order to perform. And that helps to detect again why basically the application, if you have like out of memory exception or sort of. And then we have lock, thread, halt, stop the word profiling, which is when you have, you can augment and instrument the workload profiling with additional information in order to understand why your thread, why your process basically taking that much time and why. And then heap profiling, this is probably obvious. It helps to understand what is in your heap and why and whatnot. And then there are two types of profiling. We'll be using what used to be profiling, we call now traditional profiling. That was more using agents and running off CPU. That is something that you add, running side by side or next to your application, either embedded into your application or running side by side. And that is basically was resource intensive. It needs to consume the same some amount of memory, some amount of CPU, and basically to run the application. Because it was resource intensive, we limited it before what we call production. We limited its users to QA pre-production environment and let the production environment be happily run by itself. And the hope that we basically can reproduce the same issues that happen in production, in pre-production or QA or staging environments in order to detect what's happening or recreate the same thing. So they were resource intensive. They necessitate some modifications, especially for the instrumentation. You basically need to augment your code, do some changes in order to collect some data. They provided limited visibility, especially if in distributed systems where you have multiple services. Having this cross view is challenging. And then missing symbols. When we talk about profiling, we talk about symbols, and we will get into that in a minute. And then Josh Long, which is a dear friend and Spring developer advocate, always mentioned that production is the happiest place on earth. Production is where you meet your users, where you meet your customers, where your code goes to serve what it's supposed to do, to basically deliver a feature and make your users basically happy and deliver value. So having things pre-production, whatever that environment is, that is not production, was challenging because that's where the real action happened. And having limited visibility, especially when it comes to profiling, was challenging. Or you can have the additional cost of allowing more memory, paying more to run those agents in production. And then came continuous profiling. And continuous profiling is take the same concepts from profiling, which is trying to decipher what is happening, trying to gain an understanding into your infrastructure and application as well, but add this continuous part to it. And this continuous part adds some dynamism and time orientation by basically continuously collecting data from different sources, be it your application, the infrastructure that it runs on, and so on and so forth. And the important metric here that it needs to run on production. And for that, we needed to solve a lot of the issues that we had with traditional profiling, mainly the resource consumption, to be production friendly and to have low overhead over the resources needed to run those profiling into your production. And it's not a new technique, but it was not widespread as it is today, especially from the open source point of view. Google released a paper. You can scan it here if you want to read more about it, but released a paper in 2010 about how they run continuous profiling in their data centers. And it was released in 2010 and describes the architecture that they use to run continuous profiling. And we'll discuss it afterwards, but it's the exact same architecture was adopted for all the continuous profilers we have now. It was released in 2010 or published in 2010, and you can imagine that Google was running it years before that. And when Google released it in 2010, basically, it made it part of the offer in their GCP offering, and then a lot of companies follow through. Amazon afterward, and we started to see in late 2010, 2020, a lot of companies open sourcing from Grafana, from New Relic, and so on. And we'll get all of them in a minute. So what is the generic architecture of continuous profiling, especially a modern continuous profiling that we have today? So we need to gather the data. That's the first thing we need to do. And for that, you either instrument your application, add some code in order to send the data to specific endpoints, specific API in order to collect those metrics. Or you can have a lower overhead agent that basically collect all those information and send them back for ingestion. So we collect those data and then we ingest it, try to add some remove the symbols basically because we need them. We don't need them. The machine is basically understand zeros and ones. It doesn't need the symbols. Symbols are basically think of it like a contact list in your phone. So if you have only numbers, you couldn't know which number belongs to what person. So you add names, but basically aliases in order to understand what number to which person. Exactly the same thing comes with symbols. The machine doesn't need them, but us, when we collect them back, we need to understand this issue happened in which line and why. And then we collect those profiles, and then we need to store. We need some sort of storage, and this is generally challenging. And one of the big things that continuous profiling came with, we collect. There is the continuous part that I mentioned, and that means we collect a huge amount of data. So how to save the data, how long we should save it, how we can optimize it and condense it and zip it in order to just store it for a long amount of time, and then we need a way to visualize those things. We store the data, we have it. We need a way to query it and a way to visualize it. And the image there is from Pixie, which is a cool open source tool that I'll mention in a minute. And then I touched upon that previously. So it's basically we collect the profiling information. We need to do some analysis to it, filter it, and then have some means of visualization and querying also in order to get it. Types and techniques. So to collect profiling information, we either do it sampling, which basically after a constant amount of time. After a T, we collect some information and then we send it back for profiling. Event-based approach is basically you are just interested for some events. So basically when you listen for an event, let's say, for example, if you want only interested in queries to a database that take more than, let's say, 300 milliseconds or half a second, right? So you basically only listen to this event and query and get information about why it's actually taking more. Instrumentation profilers, you instrument your code, your logic in order to send the profiler information. And thresholding profilers basically to collect outliers, everything that helps to run your application. Challenges when it comes to continuous profiling, it's for me, it's definitely the data storage because you are collecting a lot of information continuously, 24/7. You need a way to decide on how much data you would need. And different solutions have different ways to deal with it. But that's something you would definitely need to discuss and figure out when it's moving to continuous profiling. Symbolization, we talk about it, but that's kind of something from the past now. But you may run into symbolization issues and making the data that you get back, especially in terms of struct traces maybe, that is meaningful for you. Correlation with other signals now is getting better, and I mentioned it at the end of presentation. OpenTelemetry is adding profilers, so we will have kind of everything OpenTelemetry as basically the de facto standard in how we compose everything, logs, traces, and metrics. They added now profiles, so if you're using OpenTelemetry, you can correlate everything now. Widespread adoption, it's moving better now than it was a year or so back because of how the industry is moving forward, and a new technology that we will talk about, which is eBPF. Why you would be interested in continuous profiling? One of the main motivations is basically cost saving. Your application, deployed the first version of your application, it's running fine. But then, as you added more features, you added more code, and then you added more resources, basically. So the hope with continuous profiling is basically how we can optimize our code and basically to free up some resources, be it CPU, memory, make the code run faster, and reduce the amount of infrastructure and resources the application need, and that taking it back, squeeze your application, condense it so it can be run in an optimized way in your infrastructure, and that will help basically to get the resources back. And then when we talk about resources, we definitely talk about cost as well associated with it. With continuous profiling, so when you move to continuous profiling, what happens is you have those metrics that you collected. So you deploy the new version, you want to understand how it's behaving. You come in next day, it's not an incident yet. You come in next day, you notice that there is that trend change, be it the garbage collection is behaving weirdly, CPU is more, memory is more. So you basically can compare the previous version with this version, like yesterday data with today's data, and have this back-to-back analysis. Understand that your application is slowly degrading in performance, be it in CPU, be it in memory, be it in whatever performance metric we're looking at. You did impact. That will help you go back to the code, try to track where basically your CPU memory is most affected, and then fix that and optimize it. So you're having this better feedback loop with your code once you deploy it until you get it back, trying to continuously improve your code using continuous profiling before it happens an incident, before it make it to be an incident. And then with continuous profiling, the hope is we move toward more proactive troubleshooting. So we detect incidents. Well, we never do, but yeah, that's the hope. More proactive troubleshooting detects bugs before they become incidents and break your production down. And by reducing the number of incidents, you reduce the number of downtime because the less incidents you have, the less downtime the users will experience. Resource utilization, I touched upon that. Performance regression detection, I touched upon that as well. And holistic view across the entire tech stack, within your application and the infrastructure that it runs upon, which helps to also improve the application performance. Acquiring profiles. So there are two ways, either language specific, and you have different profilers for different languages. Here I mentioned some. GTK Flight Recorder is the known one in Java world, but if you use different languages, there are definitely some. Save points, that was an issue kind of few years back, but worth mentioning though. So save points is basically checkpoints within the GVM. So for the GVM to perform its work, this is more Java specific here, but probably there are others in other languages. But for the GVM to perform its work, it basically needs to reach a stable point. We call those save points, but you can think of them as checkpoints. So the GVM is running, and need to make sure that it reaches a safe point where it can basically stop the word or perform some action. Not stop the word, but perform some action. And that save points introduces what we call the save point bias. So imagine we have this number of objects, and then you called your profiler in the green arrows. But the GVM would need to reach the save point before it returns this data back. And then you would have the save point or biased view, because you are not getting the green arrows, you're getting the view from the green dots or the red arrows, because the GVM would return this information back, for example, dump threads, dump traces, whatever. It returns them after it reaches the thread points or the save point. Save point, not thread points. The save point or the checkpoint. So you would have a save point by instance. You are not getting the information that you requested, but you requested that the GVM will give you after it reaches the save point. It becomes worse after aligning. Aligning is really good. It helps to condense your code and make it run in an optimized way. However, it condenses everything, including the information that you requested. So when requesting profiling information, you may end up with a biased view. That's something to be aware of, but it's not an issue in the JDK fetch recorder and async profiler. It's not an issue from the past, but something to be aware of. Probably you might step up on. So you either have language-specific agents or profilers, or use a new Linux technology, but yeah, it was introduced years back, called eBPF. So eBPF is a framework within the Linux kernel that enables making the Linux kernel programmable. So you write code in your high-level programming language, and eBPF will have within its framework a way to make it run within the Linux kernel, attach it to the Linux kernel, and make it run as it was written from the very first time into the Linux kernel. Yes, so I was hoping that I included this diagram. So you write your program, and in the eBPF we have the user-land code and the kernel code, but we'll be focusing on the kernel code. You write some kernel code and you compile it, and then we end up with a bytecode format, similar to what we have in Java. And then we try to load that code that we wrote in C or Rust or other programming languages to the kernel. eBPF is an event-driven program, so you mean that you would attach your program to an event. Here we're attaching to a syscall, but you can attach it to network events, disk events, whatever. So you attach it to an event or a hook point, and then it passes through the verifier. That's what ensures basically that the eBPF program that we're loading to the kernel is actually safe and secure to run. And then once it's passed the verifier, it gets JIT compiled. So the bytecode version gets JIT compiled into native code, and that gets loaded into the Linux kernel. So your program that you wrote with C, Rust, whatever, in your high-level programming language gets compiled in the end and run as a plugin, as a module next to the Linux kernel. And whenever those events that you are listening to, it will be handed off to you for treatment. Like if a network request coming in, and you are interested in it, so basically the kernel will hand it over to you, run your program, and then it will continue its execution or not. eBPF is a little bit more complex than that, but we will not have time to go through it, but just to have an idea about how it works. I mentioned that it's event-driven, and there are hook points, which is the events that you are interested in, and you can basically trigger, monitor everything, because it's within the Linux kernel. Everything runs within the Linux kernel, so we have visibility over everything. And the eBPF was originally designed for network, but the idea worked really well that was extended to other things, including profiling. So a lot of open source tools took eBPF and then moved it to profiling. And we have different open source solutions here. Pixie from Øredev. It's more than a profiling tool. It's a full-fledged observability tool, but it has profiling within it as well. Periscope from Grafana. So Grafana has a lot of open source tools. Periscope is one of them that is focused more on continuous profiling. And then Parka. Parka as well is continuous profiling tool, low overhead. They all run within eBPF. So the low overhead, they all claim that they can run under 2% or have an overhead of 2%. Some of them less. And that's because of the eBPF. So they run programs they run eBPF programs, you write modules, runs with the Linux kernel really fast, less intrusive than having an agent. And then they send this data back to analysis from to their tools, basically. And then, yeah, just to show a trend, Periscope is leading the way from Grafana there, but Pixie and Parka are following up closely, especially Pixie is, I think, a CNCF sandbox tool. Kind of running out of time, but just to go over the architecture of each and every one of them. Parka, either you can have your own agent, again, blackout, or you can send your agents to an HTTP endpoint, and then it runs through the Parka server that does the analysis, and then send it to a Parka UI. Periscope follows the same thing, but Periscope have the best of both worlds. So it has its own agent for different languages. For Java, they use Java Flight Recorder, but it uses eBPF as well. So for every language, they have an agent that you can run, or you can build your own profiler, or you can use eBPF. So it's more focused on giving you the best option, be it eBPF you want or language-specific agents that you can run, but it follows, again, the same architecture. Finally, Pixie. I found this image really ugly. Sorry for that. You need to change it at some point, but it's exactly the same thing. An agent that it runs purely eBPF this time and runs through the brain of Pixie in order to collect the data and you enable you to visualize it. Looking ahead, I still have 2 minutes or 3 minutes. eBPF as a unified collection method. So eBPF is slowly gaining in popularity, especially with more eBPF-enabled hardware. So one of the features of eBPF is what we call the offloading. Offloading now is only enabled for XDP, which is one of the network functionality in the Linux kernel. Express data path, which means that you can handle the network traffic or the network request of CPU. If you have a hardware that supports eBPF offloading, you can have your eBPF program runs in that hardware. In the case of XDP offloading or XDP, it runs in the network card. So you have eBPF program that runs in the network card, and the request, the network package will be handled off CPU before even it reaches the CPU, which is a great win. So the more hardware support eBPF offloading, the better, because you are handling things off CPU and you're not damaging the performance of your applications. It still proves that is kind of secure, less intrusive than other tools because it's within the Linux kernel, more standard, and more companies are implementing eBPF. So eBPF is kind of leading the way in order becoming a standardized way. And it has a lot of popularity within the cloud native community, be it in networking, monitoring, and profiling. eBPF is gaining a lot of traction there. And then I mentioned OpenTelemetry in the very beginning. I did this presentation a few times before. This issue was open. It was just closed a few months back, I believe. So OpenTelemetry added support for profiler, for profiling, and is going through standardizing basically how profiling is collected. So with OpenTelemetry, which I suppose probably a lot of people here are using, you can collect all the pillars of observability. That was it, and I have 1 minute for question. Any questions? I like Pixie. I find it more intuitive and easier to use. Have a cool UI. I have a demo because this is a 60 minutes or 50 minutes presentation that is run here. It's already running, but unfortunately I won't have time to run it. But it basically shows having a code that you can compare multiple regions and multiple tags that you can add. This is using Periscope from Grafana. It's basically using graphs in order to find the bottleneck. But the demo is, I suppose it's here. It's online. Please check it out. It's kind of give an understanding of what you can perform with continuous profiling. Okay. Thank you. Okay, thank you very much.